All right, recording is rolling. It's Tuesday, March 28th. So just gave you guys a page that looks kind of like this. On one side has a bunch of circuits, and on the other side has, well, more circuits, but we're going to dig more into them, do some like waterfall models, figure out what's the voltage across each resistor, what's the current through each resistor, what's the power output. Try to figure out. Now, this is going to take us a few days. So there's a ton of stuff I want to tell you guys. I know we just started a new topic yesterday, so give you guys a quick review here too. Talking about electricity. There's some tools I want to show you guys how to use because I do have a lab lined up, but I might have to push it off to Thursday. I'm thinking based on how things paced out last class. I mean, there's just a ton of new information, right? So yeah, let's I want to show you guys the multimeter, voltmeter, ammeter. Here, we'll do a bunch of little stuff today, right? As much as we can. So give you guys a quick recap of a bunch of new stuff you guys saw yesterday. So we're switching over to electricity. So we've got point charges. You can measure in coulombs. If you give that a certain flow rate, you can get a current measured in amps. 1 amp is 1 coulomb per second. Now, what causes a current to flow is some kind of potential difference, also called a voltage. Classic example of a voltage source could be a battery. Here's 1.5 volts. Here's 9 volts. Okay? Break out a cell phone charger later today that has, here's a cell phone charger. It's like 5 volts. Okay, that's on it. We'll look at that later. You want some kind of resistance in your circuit. If you don't have a resistance, you get a short circuit, which just drains your battery really fast. We're going to use these Christmas lights as resistors, right? Hey, I wonder how many ohms of resistance is in this Christmas light. We might find that out later today. And then, how bright is that bulb going to burn? Well, that has something to do with the power. Right? What rate is it consuming energy, say, from a battery, from the grid, from through the charger, and watts. Don't worry about these green ones at the bottom yet. We'll hit those probably next week. I'll touch on this. We got point charges. What's the force between those? I should have made a poster also for electric field. If you just if you focus just on one point charge, you just get electric field as KQ over D squared. Did I show you guys this yesterday? This? Oh, okay, yeah, I thought I missed this. Okay. Now this is a magnet, so I can show you guys a magnetic field. So it's a similar type idea. Right? Let's look at magnetic field lines. Now, one difference between a point charge and a magnet is that magnets always have 2 poles. There's always a north and a south, so a little bit different. But right here. Okay, you guys see all these metal bars in here? Just like free to like shake around. Okay. Go away, put the magnet on here. I can tell you guys where the poles are too. So one pole is right here, and the other pole is here. So this might be the north, and this might be the south, or maybe those are backwards, but it's one version of this. Okay. So line this up. You guys see the magnetic field lines? It's like they go like this. Right, and then on the side. So it's trying to connect like north to south. I guess that like move this around. Okay. What if I just put like one pole straight up? So that might be just like the north pole right there. Shake this around a little bit. Okay. See, it's like radiating out. Okay. So we're getting different cross sections, right? Different cross sections of a 3D magnetic field going on. Okay, guys there. Okay. So not exactly the same thing as a point charge, but has some commonalities. So the side. Okay. All right, then some of these new terms, like what is voltage, what is current? This all clicked into place in my mind anyway when I was taught this analogy. So voltage, think pressure. Right? So I got a battery trying to push electricity through a circuit. Right? The current that actually flows, think about kind of like gallons per minute, cubic meters per second of water flowing through a pipe system. This is just an analogy, but it works really well. Right? How much resistance is in a wire? Well, how long is the wire? What's the cross-sectional area? What material is made out of? Might do a lab on that, possibly. Right. Here's what resistors look like. Here's how to read them. It's just side details. But here's the big stuff we care about, big important stuff. Ohm's law, really big important idea right here. How much current flows through a circuit? Okay. Well, it's proportional to the voltage source. If you triple the voltage, you're going to triple the current. Okay. But it's also inversely proportional to the resistance. The more resistance, the less the current flows. Okay. That's called Ohm's law. Bam, right there. Okay. Let me skip a few of these. Let's look at a flashlight. You guys remember the flashlight schematic? A battery is an example of a voltage source. A light bulb is a type of resistor, so this could represent a flashlight. Got a switch right here, bam. Ohm's law. How much, what rate does energy flow, right? Let's say what's the power in watts. Okay? Joule's law, you could do I times V, you could do I squared times R, you could do V squared divided by R. Right? I is current, V is voltage, R is resistance. Okay? These are all three different perspectives on the same thing, depending on the context of the question. Sometimes one's easier to navigate than the other. Right? So they'll all give you the same answer. Analogy, right, with Joule's law, right? Power could be flow rate times pressure. Think of it like that. Also works out in terms of units. Right? Flashlight. I showed you guys a few Paul Hewitt demos yesterday, and at the end he started wiring light bulbs across a car battery, 12-volt car battery, different ways. The first thing he did was he put them all in series, like one after another. And every time he added another one in series, what happened to the brightness of each bulb? Yeah, it got dimmer and dimmer, right? Now, from the point of view of the battery, it was as if the resistance was going up, 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 up. So it was pumping out less and less current. That would be hand in hand with Ohm's law. Right? And every time you add on a resistor in series, just one after another sequentially, you can just very simply add the resistances to get the equivalent resistance. Right? But then he switched and wired them like rungs of a ladder, which is in parallel. And this is where the current splits. So here comes the current flowing around. And oh, I see a junction right here. So the current has a split. Current right here splits. Right? Yep. A good analogy for current is traffic flow. Say if there's a parking garage here, right? You drive your car out. I'm going to drive around town. Okay, I'm ready to drive back. Right? So I got to drive through some stoplight. Well, you don't have to go through all three stoplights. You pick. Right? Some traffic's going to split this way. Some traffic's going to split this way. Some traffic's going to split this way. Right? And then it all comes back together. Right? That's talking about like current in amps. Right? It's like traffic flow. Right? And the equivalent resistance. Well, the more resistors you add, remember each bulb maintained its brightness. So that means that every bulb you add on, now the battery has to send out even more power, right? Even more current. So the equivalent resistance is getting actually less and less and less. It's like every time you build a new road in parallel, you're giving more options for the traffic. That actually decreases the total resistance, right? Makes it easier to drive. Right? And here's the math of this. You can say, you can use this reciprocal method. 1 over the total resistance is 1 over each resistor added together. Okay? Now, if you only have 2 resistors, then you can use product over sum. You can't do product over sum for like 3 at a time, but you can do like 2 at a time and just do 2, 2, 2, 2, 2. That's okay. Right? So product over sum works for 2 at a time. All right, we're about to run into an example of that. All right, Kirchhoff's rules. I think I'm going to save this for later in class today. And of course, I got a bunch of other posters to go through too, but one thing at a time here. Okay? So it's a quick recap. Actually, speaking of resistors in parallel, I have a question that at a glance looks like it has nothing to do with electricity, but it does. It's mathematically equivalent to all that. Say there's these 2 guys that want to paint this fence, okay? And so I'll call them Alan and Bob. I see Alan and Bob. Okay? Now, Alan, if he worked alone by himself, he could paint the whole fence in 3 hours. Okay? Bob, if he worked by himself, he's a little slower. It would take him 4 hours. They're pretty close, but not exactly the same. Okay? But what if they teamed up? Say, hey, let's paint this fence as a team, right? How long is it going to take them to paint the fence? Ooh, aren't those 2 guys working in parallel, right? There's nothing like sequential, like I'll paint the fence, and then you go paint the fence like a different color. If that was the case, you do 3 + 4 is 7 because that's like in series, right? But no, that's not the case. They're working in parallel. They're like helping each other out as a team. Okay? So does anybody have a pretty good guess how long it's going to take them? Right? It's the same thing as 2 resistors in parallel. Oh yeah, go ahead. 1.71 hours. There you go. Right. Just product over sum. Yeah, it's 1.71 hours. Okay. Or actually, here's a good way to frame this. What if they actually did work at the same rate? What if it was like 3 hours and 3 hours? Then wouldn't it obviously take them like an hour and a half? Right. Or what if it was 4 hours and 4 hours? Wouldn't it be 2 hours? So the answer has to be somewhere between an hour and a half and 2 hours for this particular set of numbers. It has to be inside that window. Right. Oh yeah. So let's get to what Pratt just got to. Right. So show you guys here. 1 over the total time. I'll use capital T for total time. Okay, is 1 over Alan's time plus 1 over Bob's time. You can use this because they're working in parallel, right, helping each other do the job faster. Okay? Now I'll solve this in terms of variables first, just to show you that this does equate to product over sum. Can you guys do? Because you can just plug in the numbers and use the calculator. That's fine too. Okay? Can you guys get a common denominator? Could you do plus Bob over Bob? Whoops, so times. It should be times. Okay. And then 1 over Bob times Alan over Alan. Okay. That's how you get common denominator, right? Okay. Because that's equal to 1. That's equal to 1. So you're not really changing anything. So 1 over the total time is, well, that'd be Allen times Bob would be Allen times Bob time would be the denominator. We got Bob plus Allen. Or I could just say A plus B, Allen plus Bob for the numerator. Okay. But there's one last step. And the last step is you have to take the reciprocal because this is not the time. This is 1 over the time. So take the reciprocal. The total time is, oh, look at that. It's the product over the sum. That's product over sum right there, isn't it? I see product over sum. And so let's go ahead and plug in the numbers. So the total time then is going to be 3 hours times 4 hours over 3 hours plus 4 hours. If you like, you could call that 12 on 7. The unit's still hours. Okay, looking at 1.71 hours, okay, which is inside that window, that boundary, those boundary conditions. Like if you didn't know how to solve this, you could at least figure out, well, it has to be more than an hour and a half, but less than 2 hours, right? We figure that out anyway. Okay. It's not exactly halfway in between, but somewhere in there. Okay. All right. All right. You guys good so far? All right. So 2 resistors in parallel is the exact same math. Okay. All right. Let me break out this multimeter because I do want to go over those problems on that page I just gave you guys too. But at some point, well, I did have a lab lineup tomorrow. I might have to bump that another day, just how things are pacing out. But it's good to know how to use these tools anyway. So that was it. So I got this this multimeter. Now, multimeter means there's multiple things you can measure. And I got this toggle switch. There's all kinds of things I can measure possibly, right? Okay. So let me zoom in here. Okay. Oh, on this left side, I see something to do with voltage. I see like a bunch of V's. So it's like 600 volts, 200 volts, 20 volts, 2 volts. Okay. And as I switch the toggle switch, all that's changing on the screen is the decimals moving. So if I had a large, if I had like hundreds of volts, I might want to use that one. If I had like tens of volts, maybe that one. If I had like single volts, maybe that one. If it was like a fraction of a volt, maybe I want to do that one. Okay, guys, yeah. Okay, so that's all volts. Okay. There's also 2 leads, right? But there's 3 places to plug in. I pull these out. You guys see like 3 places to plug in, right? So always take your black lead and plug it into one that says COM. So that one you can just like permanently leave there. You don't even have to take that one out. Okay. But whether you're measuring voltage or current, there's like some internal wiring where it's actually going to measure it different ways. Okay. So this was plugged into this one for voltage when I had to switch over to voltage. Okay. But if I want to switch to current, I got to make 2 changes. I got to pull this out, pop it in here. So one says like amps, and then switch this toggle over to there's 2. This one says milliamps, one says amps. So I think it's just a decimal place thing again, right? Okay. So something to do with amps. How many amps? Okay, like an ammeter for the current. Okay. And then if I actually want to measure the voltage of the current, I actually have to wire it one of 2 different ways too. So let me switch this back to voltage, and I'll do a live demo with you guys. So here I have this extension cord that's plugged into the wall socket right now. Okay. Now, see if you guys know this or remember this. How many volts is this supplying right now? How many volts? 120, right? 120 volts. Alternating current from the wall socket, right? 120 volts. Wait, sorry. If you're looking at this, you're probably thinking 5 volts, right? Okay. You're right, because this is a cell phone charger. The cell phone charger is 5 volts, right? Now, suppose I wanted to test, is this really 120 volts, right? So I switch this over to, right? Now, do I want to take these 2 leads and jam them into 120 volts AC? The correct answer is no. The correct answer is no, right? So when I give you guys these lab materials, you guys know electricity is dangerous, right? It really is. So if you go jamming these into here, you might get a big old fireball and like burnt hands. Okay, so nobody wants that, right? So let me check one more time. Okay, how many of you guys are going to plug these directly into 120 volts AC? That's the correct answer. Nobody's going to do that, right? Everybody got that? Nobody's going to do that, right? Everybody got that? Okay. But if I plug in the cell phone charger, it's going to drop down to 5 volts DC. Okay. Now, here's my 2 leads. Are these leads safe to touch now? Yeah, they're safe to touch. Right. In fact, 5 volts, that's even less than this. This guy's 9 volts, right? I can't even feel that. So these are both DC at this point too, right? Okay. So here's 5 volts, here's 9 volts, right? So yeah, it's okay. I'm show you guys a little bit about this charger. Zoom in, fix my camera real fast. wires all over the place here. Okay. So zoom in where you guys can see this. I was going to turn on the camera, but what input and output are we looking at here? So it's a little blurry. You guys see where it says input alternating current goes anywhere from 100 to 240 volts. Oh, well, that should cover all the main world standards, right? Anywhere in North America, you're about 120 volts, but plus or minus a little bit. Right? The European standard, like if you go vacation in England, is like 240 volts. Okay, so 120 in the United States, 240 over in England. Okay, and then what about the frequency? Because remember, alternating current oscillates back and forth with some frequency. Do you guys remember what the American current frequency standard is? 60 hertz. Yeah, 60 hertz. There you go. Okay. And oh, look at this. This takes either 50 or 60 hertz. 50 hertz is the European standard, right? So over in England, they're on 50 hertz, and we in the States are on 60 hertz. This will take either one of those, right? No, that's all input. But then my output here is 5 volts DC. You guys see 5 volts DC? Okay. So let's go back and try this. Back here, bam, right? And then, zoom out where you guys can see. Let's go on here. So I got this plugged in where I can read volts. I got this toggle switched over to volts. Maybe I'll go one more decimal place because I'm expecting 5 volts. Okay, so yeah, get that right there. Okay. All right, and then I'm going to take these two leads and attach black to black and red to red, which should give me a positive value, black to black and red to red. Okay. Oh, look at that, 4.94. Okay, you see 4.94 volts. Hey, that's pretty close to 5 volts. So we're doing good. What if I switch these? What if I do red to black and black to red? I get a negative. It's like negative. And also the number changed a little bit, but basically negative 4 point something volts. Okay. What if I want to measure current? Now, if I want current, I have to hook up I have to make a few changes. I have to bring in a resistor. Right, but let's get this thing lit up. See what this looks like. Ooh, look at that. Ooh, it's bright. Christmas light. Okay. Okay, so I have to take this, pop it out, pop it right here. Change this toggle over to the one that says, well, the other one says milliamps. So how many amps is this going to be? Right. Ooh, hey, I wonder what's the resistance to this light bulb, because we could probably use Ohm's law and whatever reading this shows to figure that out. Right? And there's one other change I'm going to do, which is I'm going to hook this up in series rather than parallel to measure current rather than voltage. I'll draw this out for you guys too. So what I just said, that makes sense. Okay. But what I'm going to do is force the current to flow through the multimeter, like through the ammeter, which was not the case when I was measuring voltage, but it is when I'm measuring current. I'm getting 2.3 amps. You guys see 2.3 amps? Okay, you guys see that? Okay. Okay. Now I know there's a lot of little wires going on here and fingers in the way. It might be hard to tell exactly what's hooked to what. So let me draw this out for you guys and then do a little bit of math and figure out what's the resistance of that bulb. Okay, figure out a bunch of stuff here. Okay. So if you have a voltage source, right? I mean, this is really the symbol for a battery, but just say some voltage source, right? Okay. Okay. And say I have one resistor on this. It could be like that Christmas light. Okay. And here, let me break open the circuit. Okay, and I'll show you guys why. Okay. So right now that's an open circuit. There's no electricity going to flow, and that bulb is going to be turned off. Right? That'd be case. Okay. But the reason I broke this open is because the last thing I showed you guys was how to measure current. And you measure current with an ammeter. So when I switched that toggle switch to the one that said milliamps, that was an ammeter. Okay. Okay. You have to hook the ammeter in series. You have to force the current to flow through the ammeter. Okay. So this ammeter to measure the number of amps that's a current, okay, is connected in series. Right? Is that how the current has to flow through the ammeter? Right? But that was not the case when I was measuring voltage or potential difference. Here's how, and I did that too. Remember, I got like 4.9 volts, whatever. Okay. Here's how you hook up a voltmeter. Okay. So your voltmeter is connected in parallel. is it's looking for a potential difference. Is that? So saying what's the voltage here versus the voltage here, and there's going to be a voltage drop across that resistor, right? Is that? So you hook those up different ways. Right, we're good. Now I hooked this up and I got how many volts was it? 4.9 volts, I think. 4.7. Okay, let's do it. Let's call the potential difference the voltage 4.7 volts. Hey, was it getting? What was it getting for this? Like 2.2 amps, I think. Let's call it 2.2 amps. So the current is 2.2 amps. That calls potential difference. Ooh, can we use Ohm's law to figure out what's the resistance of that bulb? Okay. So you do I equals V over R, or you could sometimes you see it this way, V equals IR. Okay. But if we're solving for resistance, isn't resistance equal to V over I? That would also be true. Okay. So I've got 4.7 volts. I was just a calculator, right? 4.7 volts. The current that flowed was 2.2 amps. So I'm getting the resistance had to have been 2.14 ohms, maybe up 2.1 ohms. Okay. So the resistance of this light bulb is about 2 ohms. You guys see 2 ohms? Okay. Good so far? Okay. And then again, eventually I'm gonna have you guys do a lab or have you guys hook these up in different ways. So this might be like 2 resistors in series, like one after another, something like that. Again, do all kind of configurations with these, right? Depending on how you hook the leads. Right, here, let's try this out. Get you guys thinking when you guys eventually do this. Like, what if I hook one lead here? And the other lead right here. Okay. I wonder what the brightnesses of these different bulbs are going to be. Right? Like before I hook this one right here, okay. You guys see some electricity is going to go through this one, and some of the current's going to split and go through both of these resistors in series with each other. Which bulbs do you think are going to be bright or dim? You think these two are going to be dim? This one's going to be bright? Okay. Good guess. Let's see. But it's just stuck down here. Is this dead? Oh, there we go. Ah, yeah, you're right. You're exactly right. Because they all have 5 volts over. This guy has 5 volts himself. And these two guys collectively have a 5-volt drop, but voltage drops a little bit over this one and a little bit over this one, maybe like 2.5 volts here and 2.5 volts here. That we do. Right? There's more resistance with these two than just this one alone. Yeah. So you guys get to play around with those and make some measurements and wire those up. Right? Right. Oh yeah. Yeah. All right. Let's hit that that page I gave you guys. Page. Side. All right. All right. So, oops, let's focus this. Okay. So once I had this bunch of circuits, here, organize this for you guys. The top 8 circuits, I'm just asking what is the equivalent resistance, okay, which involves some stuff I haven't told you guys yet, but I'll walk you guys through this page. Okay. The bottom 6 circuits is there's a pair of questions for each one. It says not only what is the equivalent resistance, but the follow-up question is, well, if I told you the voltage source, what is the current that flows? Right? Now that's from a macro point of view, just like from the battery's point of view. Okay? On the back side of this page are some more circuits with some waterfall models, and then we're going to set up these Kirchhoff tables and dig into the circuits, figure out what exactly is the voltage drop across each resistor, what exactly is the current flowing through each resistor, and what's the power across each resistor. So it has to do with how bright the bulb is. Okay, okay. Guess it. Okay. So let's start off with here. I think what I did last class was just went down the left side of this, so let's go and do that. So number 1. Now this one's real straightforward. There's just a battery here and a resistor here, and that's it. And the question is, what's the total resistance? What's from the battery's point of view? Now there's only one resistor. That is the total resistance. So mine says 1 ohm. So the answer is just 1 ohm. Boom, done. Does everybody have number 1 done? Just whatever the resistor is, that's the equivalent resistance of the entire circuit. Okay. Number 2. Now we've got 2 resistors. So now you have to start thinking, are these 2 resistors in series or parallel with each other? How many of you guys say series? Who says series? Series. Yeah, winner. Because the current has to flow through both of them sequentially, right? Whatever current leaves the battery, it has to all go through this one and then also all go through this one. Okay? If you guys like the traffic analogy, imagine this is a parking garage. You drive out your car. You're going to drive around town. You have to go through both stop lights, which means it has to be series. Okay? Now, if it's series, can I just add these 2 together? 3 ohms and 4 ohms is 7 ohms. Boom, done. Can you guys do that? Series, you just add them together. Here. I just followed. Bam, that row right there. Right. There were 2 resistors in series, you just add them up. Okay. Third one. These 3 resistors. Are all those 3 resistors in series? Yeah. So can you just add those up? Yeah, just add those up too. So I got 7 ohms, 8 ohms, and 9 ohms. So it is. Okay, so 24 ohms, I think, on mine. Add them all up. Okay. So you guys good so far? So just had series. Number 4. How are those 2 resistors wired? In parallel, right? Because here's one way to think about it. What would give it away is if you're driving around, you hit this junction, and then the traffic splits. So the current has to split, and not all the current's going to go through both of them sequentially. No. It goes through both simultaneously. Some of the current goes through only that one. So the other current only goes through that one, right? Okay. So, so the question again is, what is the equivalent resistance as perceived by the battery? Okay? And here's your rule, right? Isn't this like 2 guys painting a fence? 2 guys painting a fence, right? Now remember, every team member that you add on painting a fence doesn't actually decrease the total time to paint the fence, right? Or in our case with the electric circuits, every resistor you add on in parallel is going to decrease the total resistance from the point of view of the battery. So my individual resistors are 7 ohms and 8 ohms. Okay, so I'm going to guess that the equivalent resistance is somewhere between 3 and 4 ohms. Wouldn't that have to be the case? It actually have to drop. So try that out. So I'm going to do equivalent resistance from the battery's point of view is I have 7 ohms and 8 ohms. I'll just do product over some number of ohms. That's what 56 over 15. 56 on 15. That's 3.73. Oh, that's exactly within that window that I was predicting. And 2 guys paint the fence. One guy takes 7 hours. The other guy takes 8 hours. They team up. It should take them about 3.7 hours. All right. We good so far? Okay. Let's go ahead and just keep on going down the left side of this. Okay. So these bottom circuits, again, there's a pair of questions. Not only what is the equivalent resistance, but also what is the current that flows. Right. So number 9 is sort of a trick question in a way. It's the only one that's sort of a trick question. Okay. It has a short. Yeah, you guys see that? You guys see it has a short, right? Because here, let's follow the story. Let's do a traffic analogy. So you leave this parking garage, drive around town, go through a stoplight, and you hit this junction. You think, hey, I want to drive back to the parking garage because electricity is always trying to get back to home, right? Back to back. Right? And you look to the left, you see a couple of those stoplights. Yeah, okay. And then you look to the right, you see 0 traffic, 0 stoplights. Oh boy, which way are you going to go every time if you're in a hurry? Yeah, down the path of 0 resistance, right? Do you think 100% of the current is going to go down the path of 0 resistance? It will. Is there going to be any current that goes through these resistors at all? No. And this wire right here is called a short. S-H-O-R-T, a short. Okay. You guys ever heard like short circuit? Okay. Short circuit, maybe if you connect the positive directly to the negative terminal and there's 0 resistance at all. Okay. But you guys know if you take an electric appliance and you dunk it in water, it can ruin the appliance. Right? Why? Because it will short out a bunch of the resistors inside that appliance. Right? So none of these guys will even be able to play. So there's your circuit. There's your entire circuit. Hey, doesn't that look exactly like number 2? Aren't those 2 resistors, R1 and R4? in series with each other now. Okay, so I can just add these two guys together in series. So I've got 3 ohms and 6 ohms makes 9 ohms. Okay. So just add R1 and R4 because R1 and R4 are just in series with each other. Right? Guess that. Follow-up question. If the voltage source was 5 volts, which is what my cell phone charger is, 5 volts, then how much current is actually flowing through? Ohm's law time. Current is the potential difference acting on some resistance. Okay. So we've got 5 volts, and the equivalent resistance is whatever your answer to number 9 was. For me, it's 9 ohms because 3 ohms and 6 ohms is 9 ohms. So I got 9 ohms of resistance. That many amps. Okay. That many amps. Okay. You guys okay on number 10? How many amps?
Right. So it's the voltage divided by the resistance.
Yeah. Voltage divided by resistance. Right. It's Ohm's law. Right. Good. It's good with the Ohm's law. All right. Let's do this circuit, and then we're gonna flip over and look at the backside a little bit. Okay. So now this one right here, number 11, number 12. This is getting to be pretty complex. So the way you saw this is involves something that I haven't told you guys yet. Okay. Whenever you see a big complex circuit like this, there's always a process that you have to follow. And it goes like this. You cite your voltage source. So here's your voltage source. Here's your battery. Okay. Then you always fly over to the opposite side of the circuit, like right here in this case. And you work your way back towards the voltage source and you find equivalent resistances like 2 at a time. So these two, and then we're going to incorporate this guy, and then we'll bring in these resistors that are close to the voltage source. So it's going to be a process, right? A bunch of these, like this guy, like almost all the rest of these that we haven't touched yet, are all going to be process questions. You guys get that? Okay. So I'm looking at these 2 resistors. Now, if I'm only focused on that part of the circuit, I'm just going to ignore everything else except for those 2. Are these 2 guys in isolation in series or parallel with each other? I'm going to say series. Series. Yeah. You know what series? Because whatever current happens to fall on this part of the circuit has to go through one after another sequentially. Right? It all the current has to go through this one, and then that current has to go through this one. So it's series. And if it's series, do you just add them, or you like 2 guys painting a fence? Which one is it? Just add them up. Add them up. So I got 4 ohms there, and I got 5 ohms there. So for me, 4 and 5 is 9 ohms. That's 9 ohms right there. Okay. You guys figure out your equivalent resistance just in that part of the circuit? Okay. Now we're going to move back to this part. And here's where I'm going to break out some paper and redraw the entire circuit. And tomorrow I'll do more of these with you guys. And this is going to be a pattern we're going to do. I'm going to break out a bunch of paper and just keep redrawing these circuits. So I got my voltage source here. I got R4 I haven't touched yet. R1 I haven't touched yet. R5 I haven't touched yet. But R2 and R3, well, I just found an equivalent for those. And for me, it's 9 ohms. And for you guys, it's whatever you got. Okay. R5, I'll go ahead and write in right here. That many ohms. R4 is this many ohms. R1 is this many ohms. Okay. Okay. So do you guys also redraw your circuit? Right. Right. So we're still following the same process though, right? So we're leaving that, we're going back towards the voltage source. Now we're going to run into this guy. These 2 resistors, is that series or parallel? Parallel, right? You guys see it's parallel? Because whatever current is coming this way for this part of the circuit, it's going to hit this junction, it's going to split. And so some of the current goes this way and some of the current goes that way. So push through both simultaneously, you're going to treat this like 2 guys painting a fence. So 7 times 9 over 7 plus 9. Right, you guys get that? Right. That's my equivalent resistance for that part of the circuit. 63 over 16. That's 3.94 ohms. I'll round it to. Okay. All right. Okay. Redraw the circuit again. process can take a while, depending on how big your circuit is. 6 ohm there, 3 ohm there, and this guy is 3.94 ohm. Okay. All right, so now we're working our way back towards the voltage source. Now we're going to run into both of those guys. Ooh, these three, are they in what, series or parallel? Series. So can I just add those up? Add them up? Yeah, add them up, add them up. So 6, 3, 3, that's 12, 12.94. So the total equivalent resistance for my numbers is 12.94 ohms. 12.94 ohms. 94, boom, right there. All right. You guys got a number 11? Number 11? All right. All right. Follow-up question. If this voltage source was 5 volts, the cell phone charger is 5 volts, how much current is flowing, say from that voltage source, like from the battery? How much current? Okay. And then, of course, that current's going to split, go on its own journey, but we'll worry about that later. Okay. So Ohm's law time. Let's do current is voltage acting on a resistance. So I have 5 volts. I have 12.94 ohms. Zero 0.39 amps. 0.39 amps. Bam, right there. All right. Everybody good? We're good? All right. All right, so let's save a bunch of rest here for another day. Let's flip this paper over and look at the side. Okay. So I still got some circuits, but I just want to look at these from a different point of view. Okay. I've got some waterfall models set up. And also we're going to break out these Kirchhoff tables and look at exactly what's going on at each point in the circuit. Okay. So I gave you what the resistors are in ohms, and I show you guys the geometry of the circuit. So can you figure out what's the voltage drop across each resistor, what's the current through each resistor, and what's the power? Okay. I got one straight series setup, one straight parallel setup, and then a couple that are more complicated type. Okay. All right, so my numbers are, I'm going to zoom in on this one. Okay. Got 3 ohms on RC, 2 ohms on RB, and 1 ohm on RA. Okay. Ooh, so guys, what's the total equivalent resistance? Yeah, 6 ohms for me. Now for you guys have different numbers than I do, but you just add them up, right? I guess you just add them up because they're all in series. Okay. So the battery feels like it's pushing against 6 ohms of resistance, right? Okay. Next column, what's the potential difference? What's the voltage drop across each resistor? Because however many volts, like I have a 12-volt battery. You guys see I have a 12-volt battery, right? You guys see that 12 volts is the battery, right? So the voltage is going to drop a little bit across that guy, a little bit across this guy, and a little bit across this guy, right? Okay, until it adds up to 12. Okay. Now here's where I need to break out Kirchhoff's rules. Now Kirchhoff really only had 2 rules, but there's a bunch of consequences that fall out of that. Right? So point out what his rules are, and then the rest of these rows. So one of his rules was called the loop rule. The loop rule says if you identify any loop in any circuit, then the voltage always has to sum to 0. And that's consistent with conservation of energy. You guys see this more and more as we play out with these waterfall models. But like here's the loop. Okay. So I'm gonna make up an example number. Okay. What if this is like 9 volts and like a 9-volt battery? This guy right here. There's bam, battery right there. Bam. And these resistors here, maybe it's like 1 ohm and 2 ohms, so that 3 volts is going to drop across this guy, and 6 volts is going to drop across this guy. Hey, if you drop 3 volts and 6 volts, haven't you just dropped 9 volts? And then the battery pumps up 9 volts. So it's up 9, down 3, down 6. Up 9, down 3, down 6. Guess how for the loop it would just zero out? Is that right? Now that's also true. Actually, I put it under a series, but really that's true in general. So this is a loop. The voltage has to zero out. This is a loop. The voltage has to zero out. This is a loop. The voltage has to zero out. So maybe it's like 9 volts up, 9 volts down. 9 volts up, 9 volts down. Or if you're going opposite of the current, you'd say, well, it's going opposite of 9 down, which would be 9 up and then 9 down. Okay. Is that okay? So that's a loop rule. Okay. Kirchhoff's other rule is this one right here. It's called the junction rule. The junction rule says that when the current splits, it has to add up to the original current. So I'm down here in this parallel setup. So say you had like 9 amps, for example, 9 amps, and maybe it splits. Like 6 amps goes this way and 3 amps goes this way. But 6 amps plus 3 amps still adds up to the original 9 amps. That's that one. That's related to conservation of charge. Okay, it's like conservation. Okay, is that? Right, so those are 2 main rules. Now let's go back and see all these other rows that I skipped off. Right, so let's just focus on series. So the series setup that's one we're doing on the waterfall model table anyway. Right? And this one says that the current is the same everywhere. Right, so the current's the same everywhere. Right, which makes sense. I mean, think about the traffic analogy. Right, if 9 cars leave this parking garage, all 9 cars have to go through this stoplight, and also all 9 cars have to go through this stoplight, and then all 9 cars in the back of the parking garage. Right, that's all that one says. Just replace amps with cars with amps, right? Same thing. Right. And then this fraction right here, this tells you how the voltage drops. And all this says, I mean, it looks complicated, but if you think about it, it's actually not that bad. It just says that the voltage drop across each resistor is proportional to that resistor. That's all. Right? So here, if this was 1 ohm and this was 2 ohms, you guys got that? 1 ohm and 2 ohms, right? If I run this fraction, isn't that 1 over 1 plus 2 is like a third? You guys see that? So all that means is that a third of the voltage drop happens across the 1 ohm guy. And if you swap out the subscripts, you put a B here and a B here, then 2 out of 3, 2/3 of the voltage drop happens across resistor B, right? So if you have 9 volts being pumped through, then, and this guy's 1 ohm, this guy's 2 ohms, you say 1/3 of 9 is 3 volts. So 3 volts drop here. And then if this guy's 2 ohms, 2 out of 3, 2/3 of the original 9 ohms, that's 6, volts, right? 9 volts, right? 2/3 of 9 volts is 6 volts, right? So again, if this is 1 ohm and 2 ohms, and this is 9 volts, then it's going to drop first 3 volts and then 6 volts. You guys see that? So however, if it's a larger resistor, it's going to be a larger voltage drop. Okay, is that all right? That's good. Let's head down the rest of these. Okay, so if you ever have resistors in parallel, it has to be the same voltage drop, right? I sort of ran an example with you guys already. It said this is 9 volts up. This has to be 9 volts down because of this loop roll. Actually, it's consistent with the loop roll, isn't it? Okay, so if this is 9 volts up, this is also 9 volts down. Okay, so they would both just be, in this case, the same as the battery, just one's go up, one's go down. Okay, all right. Again, as we do more and more of these, this will make more and more sense. It'll click into place. Okay. The current is split. Here's the junction rule. I told you guys about that one already. Okay. Now this very last one takes a little bit more thinking, but it makes sense, but it just takes a little bit more effort. Okay. This one says that the current through either resistor is actually proportional to the other resistor. Now I'm just focused on 2 in parallel, but let me show you guys why that makes sense. So let's call this RA 1 ohm. Let's call RB 2 ohms. Is that okay? 1 ohm and 2 ohms. Okay. Guys, if you're driving around town, right? Let's say there's a stream of traffic, and you look down the street and you see 1 stoplight, and you look down this street and you see 2 stoplights. You want to get home in a hurry, and you're the only car on the road. Which road are you going to take? 1 stoplight or 2 stoplights? Well, let's go with 1 stoplight. Let's go with 1. All right. Let's say all else equals. Ceteris paribus. Right? Now, if there's a stream of traffic, let's say there's like 100 cars on the road. Okay? Most cars are going to tend towards the 1 stoplight, but after a while, now the street's going to start to get jammed. Now the other street's going to start to look appealing. Well, there's 2 stoplights, but there's hardly any cars, right? Right? And the proportion of that traffic split is going to split exactly 2 to 1 the opposite way, where most cars are going to go along the path of least resistance, right? And that's the same with the current. So here, let's run these numbers again. If this guy's RA is 1 ohm and RB is 2 ohms, what this says is that the current that goes along path A is actually going to be 2/3 of the traffic. 2/3 of the traffic goes along the 1 ohm, and the other 1/3 of the traffic goes along the 2 ohms, right? See how this current through path A is proportional to resistor B? And you could swap the subscripts. The current that goes through resistor B is actually proportional to resistor A. Okay? right? So 2/3 of the traffic goes along 1 ohm. 1/3 of the traffic goes along 2 ohms. Okay, that makes sense. Right, and then times the original current leaving the battery, maybe like 9 amps or something like that. Okay. Okay. So with all of that in mind, yeah. So if you know Kirchhoff's rules, take some practice, take some thinking, right? We can knock out these Kirchhoff tables. We can figure out exactly what's the voltage drop and the current on each resistor. Actually, bell's about to ring here in less than a minute, so this kind of have to be our pause point. But we'll do some more practice with these tomorrow, and then I do eventually want to get you guys lab, but I might have to push that off to Thursday, I think. That's a pause point.